Yeah, hello and welcome to the next part of this tutorial. So today we want to look at Apscale and how to process a metabarcoding sequencing run. So in the last tutorial, I already showed you how to install Apscale. So for now, I hope that everybody has it installed and that also vSearch is working and that Cutadapt is working. What we will look at in this tutorial is how to use Apscale, and therefore I have prepared a tutorial dataset, which we can have a look at here. So this is a dataset from a MySeq sequencing run from 2021, where we performed eDNA metabarcoding on water samples from the River Mulde in Germany, and we sequenced these data on a MySeq. And we have here, I think it's about 40 samples and 6 negative controls. And we can already see here that we have an R1 read and an R2 read, which means we have a forward and a reverse read. So this was a paired end sequencing run, which is the default input expected by Apscale. So now let's first open a terminal. So here you can see a terminal, and we now first want to move to this folder here. So I can copy the folder path by selecting copy here, or on the keyboard with Option Command C. Then I type CD and enter this one, and now we are in the folder metabarcoding tutorial. Now we first want to create a new project, and therefore we can look at the help sheet of Apscale. So we can type Apscale space -- help, press enter. So here you can see the command to create a new Apscale project is called -- create project and then a name. So let's do that. Type Apscale space -- create _ project, and now we need a name. Let's call it eDNA _tutorial. And you can see here on the right hand side, it created a new folder, eDNA tutorial _Apscale. And here we have some new folders in there and a settings file. So what we now want to do is to copy our folder or our data into this folder. So I would always recommend to do a backup of your original data, because there can always go something wrong when copying and processing files. So it's always better to have a backup where you don't do the processing on. So what we now want to do is copy our data in here in the 2D multiplexing folder. Just copy it here, and then we can see it here. So this was already demultiplexed, so this data was already demultiplexed by the sequencing company. If it would not have been demultiplexed, I would have copied in the raw data folder here, and then we have used the demultiplexer to demultiplex the samples. I will link the tutorial for the demultiplexer also in the video description. So what we now have here is our sequencing data, but you can already see that here behind the R1 and R2, we can see an _001, and then comes the suffix, so the .fastq.gz. The problem is that Apscale reads the paired end reads based on these two last characters here, so the numbers here. So if there's an _001 and an _001 here for the R2 read, it cannot identify the pairs. So what we have to do here on Mac, that's actually quite easy. You just select all your samples and then right click, rename. I already have it in here. So you select replace text _001, and then you can see here it will just remove the 001 and just keep R1 and R2.fastq.gz. just make sure this is empty here. Then click on rename and everything should be fine. So what we now want to do is go to the settings file here. You can open it, it's just an Excel file. Well, it's a bit large, but we can adjust it here. So in this Excel file, we will have 6 sheets where we can enter our settings. The first sheet is called General Settings, and here you can enter the number of cores that should be used and the compression level. So compression level, I usually just leave to 6, which is the default, and for most purposes, that's totally fine. The number of cores is automatically detected because Apscale is running in parallel, so running vsearch and cut-it-up commands in parallel so that it's much faster. So here, if you leave it by default, it will be your number of cores from your PC, a little bit adjusted so that there are some cores left so that your PC is still functional, but I would still recommend to use the maximum number, which is the default number here if you're working on your local PC. So just leave it like that and don't do any other work intense steps during the analysis. If you're on a server, I would recommend not using all the cores unless you have the server for yourself. Then let's go to the PE merging settings. Here I usually don't change anything. So we have set it to the settings, the default settings, so that basically all the reads are merged. So we have a maximum difference percentage of 25, which is super high. And then maximum differences of 199, which is also super high. So the only criterion here is that we want to have a minimum overlap length of 5. So in general, we don't do any quality filtering at the PE merging step, but the quality filtering will come later. Now we have to look at the primers and the primer trimming. And here, of course, we can't provide any default settings because the primer is depending on the research project. So for this project, we have used the Teleo2 primer, which I will just copy in here. That's the forward primer. And then we have here the reverse primer. So like this in 5 to 3 point direction. And then we can select here the anchoring. So if we have anchoring false, the primer can be anywhere in the sequence. If it would be set to true, the forward primer would have to be at the start of the read and the reverse primer at the end of the read. And if there's any other base, the whole read will get kicked out. So I usually leave it to false and will just filter reads that are not falling within the length of my fragment and the next step. But if you want to be a bit more stringent, you can also set it to true here. Then we can have a look at the quality filtering. So here we have the maximum expected error, which is basically the sequencing run quality and here filtering step. I usually just leave it to 1. It is recommended for usage. It's basically the default setting and it works really well. Then we have to look at the minimum length and the maximum length. So for the Teleo2 primer, I use a minimum length of 157 base pairs and a maximum length of 177 base pairs because the expected fragment size is 167 base pairs. So we just have a threshold of plus minus 10 here that we accept as a variant length. Then the last step here is denoising. So you can have a look at the tutorial in the description where I explain the specific steps a bit more in detail. But here for the fish data, I usually use an alpha value, which controls the stringency of the denoising algorithm. and I set it to 4 and the min size to 8. This is really depending on the marker and the organisms that you work with. So I found that an alpha of 4 and a min size of 8 works rather well for fish and vertebrates. So I usually use this one here. But this can also change depending on the data set. So with that, we are set for our settings and we can basically run Apscale. For that, we go back to the terminal and then we type Apscale. And here you can see if we want to run the entire pipeline, we can type --run Apscale. And what we now have to do is give it a path to the tutorial. And we type edna tutorial Apscale. And then we can just press enter. And it will perform the data processing. So here we can see the output of Apscale. At the first step, it will merge the reads. Here you can see the number of reads that were read into the pipeline and then also put out. And here you can see the relative amount. So you can already tell that it's quite fast. So we started at 6:23 and it will probably take about 2 minutes to perform the whole data processing. You can see here that we have an average of about 98% of PERT and merged reads. So usually a good sequencing run has an average of above 95 and even 98 is quite common. So now we already have trimmed our files, merged our files, and now the primer trimming is conducted. Here it should be about 99%, I would say, except for the negative controls, where it can also be a bit lower. And now we already have dereplicated and quality filtered and also already denoised our data in less than 2 minutes. Because that was quite quick, now let's have a look at what happened here in our data folder. So as I said, here is our raw data, our demultiplex raw data in this folder. Then in the 3 PE merging folder, the PE merged files were written, which are now highlighted with an underscore PE. Then the primer trimming was performed, so we have PE underscore trimmed. Then the quality filtering was performed. Then we have a PE underscore trimmed underscore filtered. And then a dereplication was performed. And now we have an PE underscore trimmed underscore filtered underscore dereplicated file. Then the denoising was performed per file. And here we have our ASVs in here. And then an ESV table was created. So you can see here we have 2 files. One is a Parquet Snappy file, which is a rather fast format, very effective format. So if you want to read it into R or read it into Python, I would always recommend using the Parquet Snappy file. If you just want to look at it in Excel, I would recommend the Excel file here. So if we open this now, this is our ESV table. If we look at our ESV table, we can see here the temporary ID. So in total, we have 428 ESVs. And each ESV also has a unique ID, which makes it comparable between data sets because our ESVs are denoised based on the individual samples and not on the whole data set. So this is a hash which is based on the sequence, but you can also have a look at the more detailed tutorial, which I will link in the description. Then followed by that, we have our samples and the specific reads for each sample. You can see here that our negative controls are nice and empty. and at the end we can see our sequence. Now, of course, we want to know which taxonomy is behind those sequences, and therefore we can also use Apscale, which has a new feature which is called Apscale-blast, which is very efficient in assigning taxonomy based on local databases. So you can go to GitHub and look at the Apscale-blast site here. And what we can find here is a link to the pre-compiled databases. So I always pre-compile those databases which are available on this server here. If you go to Apscale-blast databases, release September 2024, and here are all the databases available. So what we want to use now is this local database, which is a Midori 2 database, which basically is an offline version of the NCBI database. And it is split based on a marker. So we use the 12S marker in this case here. So this is a small ribosomal subunit marker, so srRNA. And we want to download this zip file here. I already did that and stored it here in the database folder. You can store it anywhere on your PC. What you have to do is unzip it so that you have this folder here with those cryptic files in there. So don't change anything about them, just leave them be. And what we now want to do to assign a taxonomy is type Apscale_blast n in the terminal, and then press enter. And now it will ask for a path to the database. And here we again have to copy the path using Option Command C of the folder that contains those DB files. Enter it here, press enter. Now it asks to enter the path to the query faster. The query faster is also in the 8 ESV table folder and the Apscale project. And you can see here, besides the ESV tables, there's also a FASTA file. So let's quickly have a look at the FASTA file in an editor. It can be any editor that you want to use. And you can see here is the hash of our ESV and its respective sequence for all our ESVs that we have in the dataset. So now let's copy the path to this FASTA file here and enter it, and then press enter again. So what it will now do is create a new folder which is named after the FASTA file, just without the FASTA suffix, and it will create another folder which is called subsets, where it will write the blast results into. The nice thing about Apscale-blast is that it's much faster because it's also based on parallelization. So it will split your original FASTA, the EDNA tutorial ESV's FASTA in this case, into subsets which are by default contain 100 sequences. So this can be also changed in the settings. Okay, now it's ready. And it will perform the blast on those 100 sequence FASTA files in parallel. So, which is also much faster than running the whole FASTA file just on one core. So you can see here that it finished the blast n for the subsets quite quickly. And it created several files, a packet snappy file, an IDs file, a log file, and those CSV files here. So what we are interested in are the CSV files. You can have a quick look here. Those are the raw blast results, which you can see here with the quality, so the percentage similarity and the e-value, and also the taxonomic assignment here. But this is yet not filtered and quite cryptic to read, so we can't really work with that. So what we now want to do is go back to the terminal, type Apscale-blast, and then filter. And now it again asks us to provide the path to the database. So we perform this again here, Option Command C, and enter this one. And then it will ask for the path to the BLAST-N folder. The BLAST-N folder is the folder that was just created, which is called like your FASTA file. So in this case, eDNA tutorial ESBs. And now we copy the path to this folder and enter it here. And now it will be super quick. It will filter the individual subsets and then create a taxonomy file. So in the more detailed tutorial, I will also show you how the algorithm works. But in short, it basically filters your CSV files, writes an Excel file, and then merges all your individual subsets to one major taxonomy table. So if we now open this taxonomy table like so, we can see that each individual ESB is now reduced to one specific taxonomic assignment. But you can also see here that our data was already filtered. So if we now sort it, let's say by similarity, you can see here that every hit that has a similarity above 97, you can also change these parameters, above 97 will be kept on species level. If there's no ambiguous taxa, I will come to that in a second. Everything that is below 97 but above 95 will be trimmed back to genus. Then we have between 95 and 90 will be trimmed to family. And then we will have a trimming to order. And then we have a trimming to class. And lastly, below 85, we have a trimming to phylum. We also have some no matches, which don't have any taxonomy and a similarity of 0. But what you can also see here is that we have some flags. So flag 1, let's first sort them here, maybe that's easier. So flag 1 means that there was a hit that could have been assigned on species level, but there was no evidence based on the e-value and similarity to decipher those two species. F1 means that one of the species had more barcodes available that had the same similarity and e-value, and it uses the one with the which was more abundant. So in this case, it was Leuciscus idus, which was more abundant in the top hits compared to Leuciscus leuciscus. Then we have a flag 2. Here, for example, those ESVs were not assigned to a single species, but to two species, because it was two species of one genus, and then they are assigned with a slash. If we have more than two species of one genus, you can see here several Corvus species, it is assigned to Corvus sp point. And then we can also see here flag number 4. If we have species of different genera, it is trimmed back to the most recent common ancestor, despite having higher similarities. So let's not keep it that way, but keep the original sorting again. But this is how the blast is performed. And now the next step would be to go to taxon table tools, for example, which I will show you in the next tutorial. And so you can see here that in less than 4 minutes, if we combine the analysis of Apscale and of Apscale-blast, we went from raw sequence data to taxonomic assignment of our data. So Apscale is very efficient in analyzing sequencing data.